Hello friends, today we discuss about the losses in transformer and efficiency of the transformer. Now we know that there are total major two type of power loss occur in transformer. First one is core loss, or you can say iron loss, and second one is copper loss. Now in transformer there is not any rotating part, that's why mechanical loss, or you can say friction and windage loss, are zero. So mainly there are two losses. Now first one is iron loss. It is also called as the core loss because this loss occur in the core, and as the core is made of iron, it is called as the iron loss. Okay, so there are two types of core losses. First one is hysteresis loss and second one is eddy current loss. Now first we discuss hysteresis loss. This type of loss occurs due to the hysteresis effect. Core of the transformer magnetized due to the alternating current, so at every cycle energy loss proportional to the area of the hysteresis loop occurs. Frequency of the AC supply is F, so this loss is proportional to the frequency of the supply, and this type of losses is denoted by WH, H for hysteresis. So WH, hysteresis loss, is equal to eta Bm raised to 1.6 F into V. Now eta is terminus constant. Its value depend upon the material, which type of material you use to manufacturing the core. Bm means maximum flux density in Weber per meter square. F is equal to frequency of the supply, and V is equal to volume of the core in meter cube. Now for a particular transformer, value of eta and volume are constant, so hysteresis loss is directly proportional to the flux density and frequency. If the value of Bm and F remain constant, hysteresis loss remain constant. So we can say that hysteresis loss is directly proportional to the maximum flux density and frequency. If these two are constant, then we can say that hysteresis loss remain constant. Second one is eddy current loss. Now what is eddy current? The magnetic field produced in transformer is alternating in nature because the supply is alternating. Now due to this alternating field, EMF is induced and eddy currents are produced in the core. So power loss take place in the core due to the resistance of the core and the eddy currents. Now this loss is called as the eddy current loss. Equation is equal to E is equal to P Bm square F square T square into V, where P constant, Bm is equal to maximum flux density in Weber per meter square, F is equal to frequency of the supply, T is equal to thickness of lamination, and V is equal to volume of the core in meter cube. So for particular transformer, the eddy current loss is directly proportional to the square of the flux density into F square. If the value of Bm and F remain constant, then we can say that eddy current loss remain constant. So we see that in these two type of losses, hysteresis loss is directly proportional to the frequency, where eddy current loss is directly proportional to the F square, square of the frequency. Okay, other terms are remain constant. Volume of the transformer core remain constant, thickness of lamination will be constant, maximum flux density will be constant. Okay, so variable part is only frequency. Now what we can do to reduce this type of losses? So to reduce the hysteresis loss, we can use, first one is good magnetic material should be used for the core. The area of the hysteresis loop should be minimum, like silicon steel. The hysteresis loop of the silicon steel is very narrow, that's why the hysteresis loss is also minimum. And second one is value of flux density should be kept low. Okay, to reduce the eddy current loss, first we can do thin lamination should be used, because in eddy current loss equation we see here T square, thickness of the lamination. If we use the thin lamination, then also we can reduce the eddy current loss. And second one is value of the flux density should be kept low. this one is common in both losses. Okay. Now a value of the flux density in transformer depend on the supply voltage. So now the supply voltage remain constant, so the value of the flux density also remain constant. Okay, so the value of the frequency also remain constant, so the hysteresis loss and eddy current loss remain constant, means iron loss remain constant. The iron loss does not change with the load, it is totally dependent on the frequency. Okay. Now second type of losses is copper loss. Now we know that in primary winding and secondary winding we use the copper winding. So power loss occurring due to the resistance of the winding is called as the copper loss. There are two winding in primary, in transformer, primary and secondary. That's why there are two type of losses, primary copper loss and secondary copper loss. Okay. So copper loss change as the square of the load current. If the losses at the full load is 500 watt, then at the half load it become 1 by 4, means 125 watt. To reduce the copper loss, resistance of the winding should be reduced, so thickness of the wire should be kept more, so the cost increase. Okay, and vice versa. Now we discuss about the efficiency of the transformer. Now power loss occur in transformer, so the transformer does not give out all the power fed to it. To account for this, the term efficiency is required. Now efficiency equation, efficiency is equal to output power by input power into 100. Now output power by what is input power? To output plus losses. So we can write here output power divided by output power plus iron loss plus copper loss into 100. There are two type of losses. Okay, iron loss and copper loss. Now output power is equal to kVA cos pi. Iron loss we can say Wi, and copper loss we can say Wc. So equation becomes efficiency is equal to kVA cos pi divided by kVA cos pi plus iron loss plus copper loss. Okay. Now we discuss about the condition for the maximum efficiency of a transformer. At which condition efficiency of the transformer is maximum. Okay. So we discuss in detail. Copper loss increase with the increase in load, but the iron loss remain constant, because copper loss increase with increase in load means when we increase the load, then current is also increased, so copper loss will be increased, and iron loss is totally independent of the current. Okay. So efficiency increase with increase in load. At some load the efficiency becomes maximum and then it decrease with further increase in load. Let us obtain the condition for the maximum efficiency. We see here efficiency is equal to output by input. Now what is output? The input minus losses divided by input. Now input power V1 I1 cos pi, iron loss Wi, and full load copper loss Wc. So efficiency equation becomes efficiency is equal to V1 I1 cos pi minus Wi plus Wc divided by V1 I1 cos phi 1. Okay. Now we further more step, V1 I1 cos phi 1 minus Wi minus Wc divided by V1 I1 cos phi 1. Now divided by V1 I1 cos phi 1 we get 1 minus Wi by V1 I1 cos phi 1 minus Wc by V1 I1 cos phi 1. Now what is Wc? Copper loss is equal to I1 square into R01. So efficiency becomes efficiency is equal to 1 minus Wi by V1 I1 by into cos phi 1 minus I1 square into R01 by V1 I1 cos phi 1 is equal to 1 minus Wi by V1 I1 cos phi 1 minus I1. Now I1 cancel, so reduce I1 R01 divided by V1 into cos phi 1. For the maximum efficiency, if we differentiate with the respect to I1 is equal to 0, then we get the maximum efficiency condition. So dn by di1 is equal to 0. So what happened? Is equal to 0 with respect to I1. Okay, we differentiate this term with respect to I1. Okay, so what happened? The efficiency of the 1 is 0 minus Wi by V1 cos phi 1 into minus 1 by I1 square minus R01 divided by V1 cos phi 1 into 1 is equal to 0. So by simplify these terms we get Wi divided by V1 cos phi 1 into I1 square is equal to R01 by V1 cos phi 1. So Wi is equal to I1 square into R01. What is I1 square into R01? This one is the copper loss of the primary winding. So we get Wi is equal to Wc, iron loss is equal to copper loss. So the efficiency become maximum at the load for which iron loss is equal to copper loss. We can say that કે જ્યારે iron loss is equal to copper loss હશે ત્યારે આપણી efficiency કેવી હશે? Maximum. So this one is the condition for the maximum efficiency. Iron loss is equal to copper loss. Okay. Now we discuss the this one is the equation. KVA for maximum efficiency is equal to full load KVA into under root iron loss by copper loss. This equation will be useful in example. Okay. Now next we discuss about the all day efficiency. Now commercial or general efficiency of transformer is given by the ratio of output power to the input power, but for the distribution transformer the figure of efficiency does not give true idea about its performance, because for distribution transformer peak load comes only for small period of time during the day, and for most of the period it is under loading, but it should be connected continuously to the supply, so the iron loss occur for the whole day, while the copper loss will vary depending upon the load condition and are very small. So the distribution transformer is designed for the small iron losses. Performance of the distribution transformer can be better known on the basis of energy rather than the power. For this, the term all the efficiency, or you can say energy efficiency, is required. So what is the equation of all the efficiency? All the efficiency is equal to energy output in a day by energy input in a day. So energy output in a day divided by energy output in a day plus energy loss due to the iron loss plus energy loss due to the copper loss into 100. Now if the load of the transformer during a day is 1 kVA at power factor of cos phi 1 for H1 hours, so kVA 2 at power factor cos phi 2 for H2 hours, etc. Okay, so energy output is equal to kVA cos phi 1 H1 plus kVA 2 cos phi 2 H2 plus H up to n. So iron loss is equal to iron loss in kilowatt into 24, and copper loss is equal to kVA by kVA square into WC into H1 plus kVA 2 by kVA square into WC into H2, where WC is the full load copper loss and kVA is the full load kVA. Now what is the meaning of these terms? Generally distribution transformer is connected to the supply at 24 hours, but there is a small period of time during the day that the maximum, or you can say peak load, is coming to the transformer. Other time the transformer will operate at the underload condition. So what we have to do, we have to manufacture a transformer like a way that its iron loss will be minimum. Okay, so this terms is required, all the efficiency, or you can say energy efficiency of the transformer. Thank you.